Our next speaker will be Jaafar Mahmoud with the talk Modern Techniques in Open Vocabulary 3D Mapping for Robotics Applications.
Hello, everyone. So thank you for the introduction. My name is Jaafar Mahmoud. I am a robotic research developer in the perception and navigation team in Robotics, SberRoboticsCenter. And today we will be talking about modern techniques in open vocabulary, 3D mapping for robotics application. In general, my colleagues already have defined the problem of open vocabulary mapping. So here, maybe we will not go too much further into details, to scientific details, but let's see somehow some real-life working application on real-life robots, how this is working. But as we have seen, open vocabulary mapping is a tool that somehow elevate the understanding of for robots to get more understanding of the semantic meaning of our environment. So it makes the perception of the robot closer to our understanding of the environment. What we are going to talk about, I'm going to talk about some general theory behind. It won't be very specific because already it has been established, and we will going step by step from metric mapping to mental mapping to knowledge mapping. And I understand that maybe right now these terms might be not very obvious, but it will along the way. And in the end, we will see some applications. So the general definition of open vocabulary mapping, as we said, is somehow to recognize and categorize object in unseen environment and build this environment so that we can somehow understand that the robot can understand and interact with it semantically and can perform tasks without teaching him, for example, what are the specific objects, what specific environment do we have, etc. So it gives a flexibility for mobile robots to operate in unknown environment and perform tasks. And as I said before, it elevates the understanding of mobile robots and it becomes closer to the human understanding of this environment. Like, for example, we understand that this object is near this object. We understand, for example, that milk is located inside the fridge, etc. So this kind of understanding, we are trying somehow to transfer it to mobile robots so that they can interact more with us. They can perform tasks that are in a higher level of flexibility and generalizability. So in general, what is mapping robotics? For long time, mapping only represented somehow the generation of a point cloud, maybe, or a voxel map or a tether map. So it was just a sense of 3D representation based on some points, maybe some features of our environment. This helped robots navigate into the environment without touching any static objects or dynamic, maybe. So in general, mapping is simply just to build a 3D map for the environment so that the robot can somehow work in it. And this is usually in robotics have a solution like SPAN or structure from motion or some kind of odometry fusion between sensors. So of course, all these solutions are different by terms of, we can classify them in terms of economical cost, how fast they are, how precise they are, etc. So that's it for mapping robots. Open vocabulary mapping, actually, it's built from two simple, let's say, titles. We need to segment anything. We need to understand the borders for every object without knowing what is this object. This is done by foundation, as my colleagues already said, by foundation models that is trained on a very, very huge set of data these foundation models right now can understand that this object, this mask for this object can identify its borders, and even without knowing what is the object, we can somehow identify the borders of this object. So this is just, right now we can segment anything we want, even without knowing what is the class of this object. But at the same time, foundation models gave us the opportunity to also label anything. So right now, only from image understanding, we can somehow link this image representation into textual representation using some models like Leap, Lava, and that is trained on image captioning and can understand and speak about what it's in the image. And so we simply right now can, we have put the text and the image representation features into the same space, and we can access from one to another like in a very effective way. And it's trained on an internet scale. As I said, it's a foundation model, so we can simply right now from an image have every object segmented, and we can label it and understand what is it without defining a closed set of objects for the robot to operate with, which gives a freedom in terms of how we are going to ask, how we are going to tell the robot to do something, and it also affects how much powerful he will be able to perform this task. As we have seen, in general, scene representation is very important to have some data structure to be able to interact with it, to save it, to traverse it. So scene graphs is one of the most used way that we can use, for example, to do this. It can it has a very good level of representation of which is located under which, for example, and every node will provide us some state, some information about something we need, some node, some image, some object, maybe some place. And the edges between these nodes will represent, in general, the interaction between these nodes. And that's why it will be easy to traverse between these objects, between these nodes, whatever the representation of. And what is even better is to add hierarchical structure to it. So it's important somehow to not only have one kind of nodes, but to have different kind of nodes. For example, we have a level 0 from nodes that only represent, for example, point clouds, and then it represents a higher level, which is object. Then it represents a higher level, which is some place, let's say a room, and then a higher level, a floor, and maybe even a higher level, a building, for example. This is if we are talking about indoor environment. And of course, we will have inner edges between each level, and we will have edges between these levels and this will make traversal even more appropriate. So, for example, if we know that something is in building number 1, we don't need, for example, to search in another building. So graph representation with hierarchical structure is simply one of the best representations that we can use to solve the problem of object retrieval or task performing for mobile robots in an open vocabulary mapping environment. So I will give a broad representation about what might open vocabulary mapping pipeline consist of. So as we have seen, we need somehow a post RGBT set of information. Of course, we can have, for example, LiDAR to provide point cloud. We can have RGBD, and we can have some SLAM or structure from motion or lidar odometry solution to provide the poses. It's usually in most of the work. Actually, we use GT poses, for example, or we assume that we already have the poses. But in general, it's good that the pipeline also include the odometry in it. I would say because it will it will provide the opportunity to give a feedback for the localization systems, so that it might be improve, for example, the localization. So building the map while doing this kind of open vocabulary mapping might be beneficial, so that we can have some feedback from the map, not only as bundle adjustment optimization, but from semantic point of view. So we have the poses, we have the images. What we do, we generate maps, we segment using anything, the foundation models, and we have a set of objects that we doesn't have a label for it. So we give an embedding in text visual space for each of these objects, and then we do something called a fusion between these objects. So we have a set of objects that have a specific point cloud, a 3D point cloud, and some embedding in some textual visual embedding space. We can fuse between these objects by calculating the similarity, the geometric similarity, and cosine similarity between these features, and merge or add new objects to this graph as we go frame by frame. After that, we can somehow try to establish the connections between these nodes, and so that we can take the textual request, do also embedding for it, process it maybe using large language models, or just have the clip representation or textual visual representation. We can use whatever model we want to traverse the graph and get the information about what we are trying to do. So that's it. Let's move to a more technical work. So right now we have a robot, and we need somehow to build a map that is open vocabulary, and we don't know anything about this map, and we need to perform some tasks. We need to tell the robot, for example, where can I buy a snack? Maybe let's go to the meeting room, grab my file from the printer, and maybe where I can sit and have my lunch. Of course, these questions, like 5 years ago, were like impossible for robots. Now are getting too much easier using these foundation models and these techniques. So in our lab, we have calibrated sensor box on a unitary robot dog, and we need to implement a solution so that we can only give this robot this task, and it will perform navigation, not only mapping, navigation to perform this task. In general, asymmetric mapping for such purposes like open vocabulary mapping, we are using two methodologies. One is visual odometry solution. We call it MASAR. It's a visual odometry solution that is based on a work called RVO. And we have edited this baseline so that it can take any configuration of visual camera, where we can have mono. If we need with neural depths, we can calculate it, RGBD and stereo, and we calculate the features and line features, and then in general, this is a very basic SLAM algorithm that gives us the poses, and it was really accurate so that we can use it for such tasks. We can see a quick example of how this is working. For example, for example, on the left, it's working on simulation data from a replica data set. The input are RGBD, and on the right we have like a fast and blurry images from a stereo camera, and it doesn't affect the robustness and accuracy of the slab. So in general, this solution was convenient to use in open vocabulary. Another method we use, which is more accurate, and for higher accuracy and large environments, we use LiDAR mapping with the opportunity to do loop closure and do map optimization in offline, so that we can build a very accurate LiDAR mapping using fusion between several sensors. And this solution was really robust, and it gives very high accuracies than the visual odometry system. And it's already adopted in our pipeline of open vocabulary mapping. So the next step is that we have this map. We need somehow to give the robot an understanding of how he can move in this environment. So simply between the open vocabulary maps that we are trying to build and the metric maps that we have, we built something called mental mapping, which is simply a set of, it's a level that consists of several points in space. And for every point, it's traversable by the robot, and it has some meta information that we can build upon it, and it will be based on the metric mapping, and in later it will help the knowledge mapping to give much higher accuracy in performing tasks and more efficiency in building the map. In mental SLAM, we to provide the metadata for each node here, we use like VLMs, like LEAP, large language model, to also process the text requests, and some open semantic segmentation models. So the work that we have based on is called LMNav, and generally we have a set. Every node is simply an image, and we have a metadata for this image, and we try to construct a graph between these images so that it will perform tasks like, for example, here, go towards a park bench and do, etc. So it will be processed by LLM, and it will go to this step by step, so that we perform the tasks in this specific order. So here we can see, for example, a 2D mental mapping representation for the SberRobotics office. Every node here consists of this meta information. We have depth map, we have panorama view, because we need to grab whatever the most more information that we can get only from RGB image. We have clip embedding, which connects the textual and visual embedding, and we have a definition of cluster graph, so that it will be later used in building of the knowledge map. And we have information about the poses and the intrinsics of all these sensors. And this mental map actually can provide a request in such a way that, for example, we can look in this graph to for a meeting room, we will get this image. For a vending machine, where is the robot, for example? Just weird requests like place to sit on the floor. It will show that you can sit here, for example, a place to sit, these two chairs, and here, go somewhere comfortable to sit. It's here in the kitchen. So in general, it can provide images in the graph and give us an intuition of how can we go there. And we can do traversal on this graph. Basically, we give him some text, and it will go there. And here we have some demo of our robot dog. We asked him to go to the kitchen, and he will generate this global path And between these dots, we use some local navigation method, local planner navigation method, and we will go to the kitchen. For example, we ask him to go to the stationery where we have some pencils and pens, and it will go from the kitchen to the stationery. So in general, it can traverse on this graph. But the problem is that we can only go on the nodes that we have already traversed. So it's just a method to provide a global planner to our robot so that it can perform some navigation on in this map. So the next level is knowledge mapping, and our solution is based on concept graph. And as we already have seen what concept graph is in one of from our colleague Dimitri, and actually this work is a cooperation between MIBT and SberRobotics Lab. I won't go into deep details of how concept graph is working, but in general, it follows the broad pipeline that I have shown before of open vocabulary semantic mapping. And the goal here in knowledge mapping is to have a level in our hierarchical graph that can represent these objects, and we can provide requests to these objects. And this is by, of course, building a graph between these objects and traverse and perform tasks based on it. What problems we have faced? Of course, most of the open vocabulary mapping systems actually try to evaluate themselves on simulations or a very well calibrated and very good data set, for example, but in real life, this is not always the case. So if we have, for example, not a very good odometry, we have some problem in depth sensor, the calibration is not very accurate, the mapping process is just a nightmare, and we cannot at all use it to provide a knowledge mapping. To overcome these issues, one of the methods that we used is somehow to, we have some points from the visual odometry, we project them into our depth maps that we have, and we try to correct the scale and the drift for these images based on the sparse set of points that we have in the map. So this is just a simple ICP algorithm that it a little bit improve the problem that we have in building if you have a problem in sensors and the depth is not very good. And of course, what helped also is to increase the level of odometry we have. For example, we tried to run this solution on different algorithms for SLAM, different like ORB, for example, and different configuration from our SLAM. For example, mono, it's not very, it wasn't very stable. We needed something better, and it best worked with RGBD configuration of our visual odometry, and of course with LiDAR mapping. So that's why right now we are using both of these methods. And another problem is that, as my colleague Dimitri said, concept graph has a problem that it's really slow, and it's in general, for big maps, we have a problem with memory. We do clusterization on base from the level of mental mapping, which is a previous level, and we build there the maps one by one, and then we fuse them together and add them together so that we can interact with the whole map in the future. And this first, of course, solve the problem with the memory, and we can parallelize the building of these clusters alongside each other so that it will become faster. Here we can see, for example, how our RGBD visual odometry works with the whole system. So here we are just trying to build a sparse point cloud of using RGBD visual odometry that is called Mashar, and it's written in our lab. And then after that, we construct, this is on real data, and we construct the knowledge map from it based on the general pipeline that I have explained before. So here we have the results after the fusion of these point clouds. Of course, here for every object, we have textual embedding. We can ask some requests in this environment, and we can notice that somehow it's still not perfect. We have some missing spaces in this environment, but this is actually a good results on real life data, because it was really challenging to make such works like concept graph works on real data, because it was really sensitive to the problems like drift in odometry, or that the depth model is not very good. So in general, here we can see that we can, for example, 1 minute, ask where is the printer, and it will show this red point cloud. Where is the vending machine, and it will show this point cloud. So right now, just using visual odometry solution with an edited version of concept graph with ICP solution, we can somehow interact with our map and perform and have an object level retrieval that we can transfer to the robot. So, and the previous example was simply on handheld dataset. Now we need to see some solution on the robot. And also, as I said before, we built the metric map using the LiDAR, not visual odometry. We have clustering on the mental mapping level, and then we build the map on it. And here we ask, for example, for a chair in a kitchen. So we go to the cluster where we have a kitchen, for example, and then we look there to a chair. And right now, because of this hierarchical level between mental mapping and knowledge mapping, we can get these requests with higher accuracy, because first we go to the general place and then we look to the object in this place exactly. The future directions, of course, is somehow to we understand that this module is also it's working on real environment hardware. It's still sensitive to cheap sensors and for odometries that are not very accurate. So we need to optimize geometric mapping. For example, if we have some fast movement and a lot of dynamic objects, we will have a problem in building this map. Also, we need to improve the embedding representation. One way, like for example, using the BBQ methods that guys in MIBT have already did, for example, which gives better embedding than the clip that we are using in knowledge mapping. And we are aiming to have a real-time performance so that we can build this map on real-time and update the object status in our graph on real-time. That's it. I'm ready thank you for listening, and I'm ready for your question. First question is how the pipeline can take into account dynamic objects. Can dynamic objects be part of the map? And no, right now, unfortunately, dynamic objects right now are not a part of the map. And basically, this is also in the near future plan, so that we can add these agents, and they need to be a part of the task performance. So maybe we can ask, for example, to give this person something on the floor or something on the table, give it to this person that is in front of you, and this person might be moving, so the robot can need to follow it. So this we will for sure add it. We have the embeddings, and we need to think of a way that we can add this agent to the map. And about the accuracies that will be worsened by the effect of dynamic objects, we can remove these objects on the level of visual odometry and in the level of LiDAR mapping, so that it won't be a problem. And in both estimation, but it will I mean, we don't consider these points on this object for pose estimation, but we consider it for building the agent in our map. But recently, no, we haven't.
Okay, thank you. We have one more question. What do you think about processing small objects for robot manipulation in your pipeline?
Mm-hmm. Yeah, that's a very good question. Actually, right now in the pipeline that I have shown, this is exactly the problem that we are having. But this is basically because I think we can say that the problem in that is really depend on how good the embedding we are using is. So for clip embedding, actually, this is a problem. For the semantic segmentation that we are using, also this is a problem. That's why we have done a research in the team of what can be another variant for semantic segmentation models that are faster and better than the ones that we are using. We are using efficient vid, by the way, in this pipeline, which wasn't exactly in knowledge mapping in the concept graph work, and it was simply SAM, which efficient bit is a little bit faster, a little bit better, but still have a problem with small objects. So I think we can improve this by providing better segmentations and better representation for these objects in terms of textual embeddings.
Thanks. And what about the resolution of this map? What is the smallest size objects that can be represented in these knowledge maps right now?
Actually, in general, it wasn't measured specifically, but we can see, for example, some objects like monitors, keyboards, some certificates, for example, on the floor, for example, on the wall, which are also not very big. So in general, it can provide it can provide a mapping for an object around let's say 30 centimeters, based on my experience in building these maps, 30 centimeters by 30 centimeters. And of course, it depends on how much we have seen this small object, because if we have seen this small object for 1 or 2 frames, then it won't be fused in the map. But if we have focused, for example, and we have been in a room and doing and we have seen this object several times, then for sure it will be fused. So it depends on how much time we use it and how good the semantic segmentation masks and the embeddings are.
Thanks. And one more question. Are you planning to incorporate some other hierarchy level, like floor, building, or maybe something like that, to make these maps more efficient in terms of accessing some part, some object, not to iterating over the all objects from your map, but like something like caching or more?
Definitely, yeah. Well, map representation as hierarchical, we are actually building this solution step by step by hierarchical representation, so that in the future we will have such smooth improvement, so that we can add several layers based on the previous layers we have. So adding floor and building levels, it will for sure will be added, and I think the traversal that we are using right now and the data structure that save this knowledge map right now will support this movement to higher levels, and as we are also moving to real-time performance, I think the traversal is really fast, even though the building of the map is right now really slow, not in real time, but the traversal that we have is really fast, because it actually goes from higher level to a smaller level. So as we have seen, for example, what I wanted to say is that the data structures that we save the map in actually support going from these levels to higher levels, just like building floors and buildings, actually, so it supports going to this structure, and also as we have seen, this structure that we are using actually goes when we have a textual request, goes from upper levels to lower. For example, when we searched for a chair in the kitchen, we didn't look for all the chairs in the lab. We only we went to the kitchen and then looked to the chair there. So this makes the traversal faster. So building the map right now is problematic, not in real time, but traversal is really fast as the data structure that we are using is optimal to this kind of. So we can expand it to higher levels, and it will give fast traversability because we go from higher levels to lower levels to perform the task.
Thank you. And one more question. How do you think, what is the most prominent bottleneck in your pipeline? I mean, not in terms of performance and latency, but in terms of metrics quality.
The bottleneck right now, I would say that it's the sensitivity to a good data in the input level. So which is not very good and not very practical for large scale solutions. We need to have a very good clean data I mean, even some small problems, some small drift, some fast movement can make this process very difficult. So this is one of the biggest problems that we have. Additional to the long time of map building at this moment. But actually, efficiency right now is not an issue because there is a very, very large space for improvement in terms of efficiency. But we need at the same time to improve the robustness and the accuracy of the maps that we are trying to build.
Okay, thank you. We have no more questions. Thank you for your talk, and hope to see you again next year.